All right, welcome. My name is Heiko. I'm living in Berlin, and I'm super happy that so many people of you are here today, even though we have some pretty tough competition in the other tracks.
I'm Marijn, I'm Dutch. I've lived here in Amsterdam for 2 years, and it's been interesting to be in this room again, because, well, I only know this as a club, and it's been interesting to be standing on the DJ booth and giving our talk.
Yeah, we're both engineers, and we work for a company called Wooga. It's based in Berlin, and we're around 250 people, and we're creating mobile games. All right, let's jump right in. Let's make some lion stands. We want to start off with showing you some of our animations, so you just get a feel for our project. All right, that's our project. In the next 45 minutes or so, we want to show you our project and talk a bit about the challenges we faced and how we solved them. We have 4 topics for you. First, we want to give you a brief overview of our art workflow, show you our pipeline a bit. Then we want to show you how we manage our assets and some of the problems we faced there and how we solved them. Then we jump into our animation system that we wrote. And finally, we want to talk about how we test. But let's start with the first step, a brief overview over the art workflow. So when we want to bring a new character to our game, we first start out with concepts. These are just little sketches that our concept artist creates to explore the animal. We draw the animal from different sides, and already start thinking about how we want to later on animate and rig the animal, so where the bones should go. This is the final concept art. And keep in mind, this is, at this point, just a 2D drawing that the concept artist then hands over to the modeler to create the model in Maya.
So the modeler looks at the concept art and creates the model for the lion. And in this case, well, it's now shown in Maya. What's good to understand here is, of course, that it can't be animated yet. It's still a static mesh. So we need the lion to be rigged. And these are then the bones for our lion. And together with the bones, together with the control curves, we have the rig of the lion, so we can animate them. Now, this is the rig for another animal. Maybe you can take a guess which one this is. It's the baby elephant, giving himself away with his trunk. And this also then is completely rigged with all the control curves.
Then the modeler takes this and hands it over to the animator. And here you see some first concepts for animations, what the animal could do in our game. Different poses, different walk cycle, a fast one, a slow one, a relax, a idle. And here you also see the signature move of the lion, which gave this talk its name. The dancing lion. And we have our baby elephant also animated here. That's the excited animation when he sees something he likes. All these animations are then exported to single FBX files using a Python script that we created. And those files look something like this. If that were all one big FBX with all the animation in there, then we always would get merge conflicts when separate people, separate animators are working on different animations, so we all split them out, one animation per file. Which already brings us to the next topic, how we manage all those assets. So the first challenge we are facing with managing the assets is that we have a lot of them. In the final game, we want to have hundreds of animations, and each animation has many different variants, and we will also have hundreds of different animals. So how do we manage that? Well, let's start with the first step. It's pretty straightforward. You've all done it a million times. You created your assets in Maya. Let's bring them to Unity. So what you do, you take your FBX files, drop them into your assets folder. You adjust some settings here and there. Then you take your assets and you create prefabs out of them. You add your mono behaviors, your components, maybe a collider. And then finally, you take all your animations and wire them up in the animation controller. Now, this process works fine when you have 5 or 10 animals. But it doesn't really scale for hundreds of animals because that would take forever, right? So, well, we are engineers, and whenever we do the same thing over and over again, we get this tingling sensation in our fingers. And what do we do? Well, we automate it. So instead of doing the same thing over and over again, we write code that does it for us, that basically handles all these steps I talked about. That is a bit of an investment in the beginning, but it saves a lot of time in the long run. And also, because it's all automated, once that setup is correct and once everything is working, it's also way more reliable than a manual project would be. And the nice thing about Unity is that you can also quickly create some nice editor UI to show that process and to give the artist an overview of all the assets that are there and if everything imported correctly.
So let's look a little bit into that. We call it the content window in our Unity project. So if you look here, you already could see it on the right. We have a list of all of our animals here. And this is basically the entry point for the artist to work with the animals. So if the artist comes in and wants to create a new animal, then here we have this plus button and can just create a new one. And when that happens, what we do in the background is, well, we take the FBX, the rig of the animal that we saw before, and we create a prefab out of it, right? And on the prefab, we put a whole bunch of components. For example, we use the Unity navigation system, and we put a nav mesh volume on the animal, so it cuts out in the navigation mesh. And now you might be thinking, OK, wait, I've seen this before, some of those like preview boxes or something. Well, they come from the inspector, right? So normally in the inspector, you have them in the bottom right. And the code behind that is rather straightforward. It's a class that you can just use from Unity. It's called the preview render utility, and it's quite straightforward. You pass in where you want to render, you pass in the mesh and the material, and also some transform data like rotation or whatever, and then you can preview your objects. And then you might be thinking, OK, how do you get to a class something like that? Like, you don't come up with it all of a sudden. Well, let's take also another example. So let's say the profiler window, right? The profiler window is a quite complex editor window. It has a lot of functionality and a lot of different things. And you might be thinking, OK, I like some of the things here, and maybe I want to create my own editor windows and get inspired by this. Well, what you can do, if you use an IDE, if you use the IDE writer, is that you can just peek into the DLL. And there's a couple ways of doing this, but for us, we can just, for example, type Unity editor profiler window, and then it will become, there we go. And then it says cannot access internal class. Well, we can't access it from code, but we can still look in it with writer, right? And basically what we do is we just take a look into the Unity decompiled DLL. And the nice thing is that you can exactly see how they do it. So we see, for example, this dragging pane or whatever it is, we see it here, or we see the toolbar, and we can just exactly see how they do it in code. So they call something like that, they call a splitter state, and here they initialize all the values. And this is really interesting because you can get really inspired by how they do things, and you can create really awesome editor windows. And you see that we also do that a lot. For example, when you see it here, we have those close buttons here, those crosses. Well, those come from the profiler window. You have this toolbar here. Well, we looked at the Unity code, and they have a nice skin for this. So you can inspire by a lot of the stuff that Unity does and take it to your own editor windows. So you end up making tools that really feel native in the Unity environment and are nice for artists also to work with. Besides that, I mean, you can use writer, right? But in the end, you just look into the decompiled code. So you could also, maybe you know this page already. It's the decompiled code of Unity. And it's quite straightforward, so you can just, it has the GitHub search functionality, so you can easily find things. So if you see something in the editor that you like, well, you just look it up, and you can see how Unity does it and get inspired yourself.
It's nice to see how the smartphones come up. So a lot of people probably haven't seen it yet. So if you add all those things in Unity, those assets can quickly add up, right? You have all your materials, you have your shaders, you have your textures, and if you have hundreds of animals, that could easily add up to 500, 600, 700 MB of your build size, right? Well, and then Apple is like, well, it's nice that you guys have 700 MB. I give you 100. Because if you're over 100 MB, people can download it on the go on the iPhone. Yeah, you might think, OK, what's so bad about that? Then they just download it over Wi-Fi. The problem is that it hurts your install rate, right? And that drives your cost per install up, right? And you don't want that, because that could, in an extreme case, make the difference between a profitable game and a non-profitable game. So you want to keep your cost of install low. That's why you want to put everything in your bundle below these 100 MBs. And then everything else, everything that is above that 100 MB, you just put in an asset bundle, right? And you upload these assets bundles to a content delivery network, or a CDN. And CDN is just a fancy word for a bunch of servers, where then users can download the data over the air, and you get this nice little small initial download. Another challenge is when you have all these assets in your Unity project, that you'll see those guys a lot, right? A lot of asset importing. And we had a previous project at Unity, at Wooga, that had really gazillion assets, and that at the end, the more assets they added, the slower Unity got. 15 seconds. That's how long it took them to switch back to Unity. So imagine you're working with Unity, everything is fine. You want to quickly check something out in the browser. You switch to Chrome, Google something, switch back. And then even though you didn't change anything, you have to wait 15 seconds, just because the asset database has gotten so large. And it got larger and larger over time. Now, how can we solve that? To find a solution, let's look at our pipeline again. At the very beginning, we start out with a Maya file, right? It's done in Maya. It's exported as an FBX. And then our automated content window creates prefabs out of these FBXs. And then finally, we take those prefabs and build them into asset bundles. Now, if you think about it, the first 3 files in that step are all source files. So once you build your asset bundles, you actually don't need your source files anymore, right? You can just take them out of your Unity project. So the setup we are using is we have a build machine, and that build machine has all the assets, all our hundreds of animals. But on your individual desktop, on the machine you're working on, you actually only need the one animal you're currently working on, right? And once you're done working on that animal, you could take that animal out of your Unity project. Well, how is that done in practice?
So let's look a bit at our Unity project. So this is how it looks a little bit simplified. So you got the assets folder, and besides the assets folder, we have this content folder. And what's good to realize here is that the content folder is not part of the assets folder, right? And it won't be imported the moment you start Unity. So let's say it looks a bit like this. We have this content folder that's not in the Unity project with the elephant baby and the lion, and we have this content folder in the middle that's empty. So one way of getting it into the project and changing it would, of course, be just copy-pasting the file into Unity, changing it, and then copy-pasting it back. But of course, this is a little bit error-prone, a lot of manual work. You could also automate this, right? You could write a script that does this for you. You could copies this file and such. But what we did is we went with symbolic links. So with symlinks, and they're in the OS X Finder, they're called aliases, you can easily create references to other folders, to other files. And we use that to refer to folders outside of the Unity project, and that way dynamically load and unload content. So what you see now is that basically the lion is, well, it's not another lion folder, right? It's just a reference to another folder on a file system level. And to accomplish what Heiko just said, is that we put this folder on git ignore. So this is your own small workspace. So if you load an animal, well, you will be the only one that sees that, or unload an animal, right? So the artist can have their small little workspace, and also the build server can have all of the animals. And we see this a lot, that our artists actually only load 1 or 2 animals and keep their project clean. And then if you don't want it anymore, then you just remove the symlink. And of course, we all automated this, right? So we all did this by code. And how that looks like, again, in the content window, is like this. Oh, I forgot to remove this one. It's not going to compile anymore. There we go. So, so here we have got the content window again. And now, for example, if we want to not work with the giraffe anymore, we can just click the close button. Whoop, it's still compiling. There we go, it's gone. And then if we want to, so what happened in the background is that we just delete the symlink. We don't actually delete any folder or something. We don't do anything fancy besides that. We just delete the symlink. And then when we click load, we create a symlink again. So it's quite a simple step. And by just creating the symlink, we refer to all of this content outside of the Unity project. So now we have all our art in the game, and we have a pretty decent solution to managing all of them and making sure that we can scale for years. And we have a nice overview of all of them for the artist, but also for us. And the next thing is, of course, to bring them to life.
Yeah, let's make the line dance. Let's talk about the animation system. And I want to start with a little demo of what our animations look like. So let's go to our content window. Here we see all our animals, where the artist can check if everything imported correctly. And if they want to play around with an animal, they just press a button. And then we automatically load a scene that we call the sandbox scene. In this sandbox scene, the artist can go in and check if everything imported correctly, if all the transitions work out nicely. So the artist can just click somewhere and make the lion move around. So what are we doing here? So the first step is, if I click in the exact opposite direction of where the lion is facing, the lion wants to turn around. So what we do is we play the little jump animation. Then while the animal is in the air, we turn him around to the exact angle we want him to go later. And then we have to be done with that by the time he touches the ground again. The next step is to actually move the animal. For that, we use Unity's nav mesh system. And in the update 5.6 of Unity, they actually added lots of great new features to that system, like, for example, the weighted areas and the area costs. And we're using all these features since the very first beta, and they're working really nice for us. One difference for us is that our animals are quadrupeds, so they have 4 legs, and they move a bit differently than a humanoid would. So what we do is we take the path we get from pathfinding and apply a Bezier interpolation to it. So we create a Bezier curve. And we tweaked that Bezier curve quite a bit to make the path actually look like a path that an animal would actually take. So we have that smooth path, and while the walk cycle is playing, we move the animal along this path. And then just before he arrives at his final destination, we play this little skid animation where he stops walking, and we, depending on the state, we figure out just the right time to do that. So in the prototype, we built a nice little state machine for that, and that is what it looks like. So you can see that in the middle there's the idle, and then once we want to start walking, we first go to the turn down here. And then depending whether we want to walk fast or slow, we go left or right. Here, that's the slow run. And then once the slow run is over, we go to stop slow run, which is this little skid. But there were some problems with this design. First, what is happening in our game is that we always have several systems that execute in parallel. So first, there's mechanism, this visual state machine that transitions from states at the correct time. In parallel, we have our own code that adds additional behavior, like, for example, turning the animal while he's in the air, moving along the Bezier path, and then just starting the skid at just the right moment. On top of that, we also have the AI layer. An AI will determine what the animal will do, and depending on the state of the animal, that behavior might be different. For example, if the animal is hungry, he might start walking around and looking for food. If he saw some food, he would maybe speed up and walk there. So there are many things that are happening in parallel, and if you worked with a similar setup before, you might have experienced the same effect. It's an effect we call the two fighting state machines. So what's happening is every time you want to add behavior, so if you want to, let's say you want to teach your lion a new trick, then you would have to add that behavior in two spots, and we needed to do that in the prototype several times. Right? You would have to add it to the state machine, wire it up correctly, and then you also add it to code, and then you also add it to the AI, right? And whenever something goes wrong, these state machines can get out of sync. So the animations are already in a different state than you think, right? For example, imagine there's a trigger that just doesn't get consumed because the state machine is already in a different state, and then when you come back, you immediately go somewhere else because that trigger is still set. So you have two state machines that are going on at the same time, and it's not always easy, and sometimes it takes a bit of tweaking, and sometimes it takes a bit of time to find out all the edge cases where those two systems can get out of sync.
And besides that, we also had two other issues, or challenges that we saw in the prototype. One of them was that we knew that we were going to have a lot of animals, right? So we knew that we were going to have a lot of animals that are going to be a little bit different. And what that would mean is that we're going to have hundreds of animators. So hundreds of animators of mechanism state machines. And we already had kind of problems with this in the prototype. So when we wanted to change something, like a transition, and we wanted to change for all the animals, we had to go into every single animator. And if you wanted to make a small change, well, you have to do that in all of them. And that was quite error-prone. Besides, we also saw that even though in the prototype it was still pretty good, those things tend to be getting quite complex. So you just have to Google it, mechanism state machine, you will find what I mean. They're huge, right? They're absolutely huge, and ours is tiny in comparison to some of them. And the nice thing with mechanism is that mostly, well, it's a super complex system, so that's amazing. And in the beginning, it is so super simple to make things. You can quickly prototype, you can quickly test out things. The artists love it, right? The problem is once you add a lot of animations, once you get more complex and it gets bigger, the state machine gets more complex. At some point, it gets so complex that it gets a bit out of hand, and it's tough to manage. And actually, I think it was last year, the engineer of Firewatch, maybe that was also here, said exactly the same, right? That they had quite complex state machines.
So when we moved to production, we thought, how can we solve this problem? Yeah. So how can you animate things in Unity? You basically have two choices. First, you can do it visually using a state machine. Or you can write code using the legacy system or the Graph API, the playable API. Now, each of these sides have different advantages and disadvantages. And which one is better for you totally depends on your preferences, but also your project you're working on. For example, Mechanim really shines in a setup where Mechanim is the only system that is driving the action. In our special case, we decided to write it in code. And I can quickly tell you why we did that. So, first thing, what we created is one unified system. Right? We don't have two fighting state machines, we just have a single one. And the big advantage of that, whenever we want to make a change, we only have to change one system. Right? We only have to make changes in one single place. And if you remember how our animations work, let me show you maybe another animal about a baby elephant. Just open up in the sandbox. So first you have this turn, and then you have the walk, and then you have the skid. And in the system we build, one system always does everything, like the walk, does play the animation, and also move the animal along the path. And that's one example of what it looks like in code. If you see here, we basically give our animals orders. These orders are just simple data structures that contain some commands. And what you can do is you can just queue them. You can just line them up and tell your animal, well, first you idle for a moment, then we want your animal to turn, then we want the animal to walk, and then we want it to skid. And like I said, each of the system does everything that is needed to make that system work. Right? Let's go back. Now, Mechanim has many, many, many great features, and it comes with a lot of power. And the bad news is, if you write your own system, you have to create all these features yourself. But the good news is, you can create them all yourself, and you can create them just the way you want them. And you can tailor them very specifically to your game, and thereby reducing the complexity of the whole system, and also make it easier to maintain. And the architecture we decided to go with is a separation of logic and data. So if you think about it, your state machine contains some logic, like, for example, what happens when, which parameters trigger which events. And then it also contains some data, like, for example, how long is this transition? And that data is usually what the animators want to tweak and play with. So we separated them. The logic we handle in code, and the data we handle in our own custom editor window, where the animator can go in and play around with the values. And we want to show you that.
So we call this the animal animation window, and it's here on the bottom. You might have seen it already. So let's see. So it consists of 3 parts, and let's take the hippo as an example. So what you can do here, and I hope it's not too small. Oh, it's actually quite big. It's quite OK, I think. So this is the way we show the transitions. So we do it a little bit the other way around as Mechanim does it. So with Mechanim, you always have a transition visualized. And by default, that's always 0.25 seconds, right? And the way we do it is that we don't show any transitions unless you override something. So by default, all the transitions are 0.25 seconds. And if you want it to be different, well, you can change it here. And we already see a couple of transitions there. But for example, what we can do is we say, OK, from the dance to anything else, we always want to take a transition time of 0.50 milliseconds. So we saw in the prototype quite a lot that we tweaked those values and that we often had to change them in a lot of different transitions, and they all had to have the same value. And by this, we avoid this whole problem altogether by just having one value for them. So we can also say the dance to the excited, and maybe, let's see, oh, this one doesn't have excited. Let's see the dance. Oh, the dance to the dance doesn't make sense. Let's say the relax. So the relax and to the talk. And then you can, like this, you can also specify transitions from one to many or from many to one. So that's the transitions part. We also have a list with animations. So here we see all the animations of the hippo. Let's just play with it so we can actually see it. Oh, not maximize it. So, and now those buttons in there, well, maybe you saw the change. They now became play buttons. So we can let the hippo come to the front. It's taking a bit of a d-root, there it is, and we can let him, for example, eat. And what is the nice thing about this is that we actually, what happens in the background is that we actually tell the AI of the hippo to eat or to do something. So we can also, so it's really nicely integrated. It's not just playing the animation, it's also doing state changes and such if needed. And of course, we can also speed things up and such. So if you want to let him eat really, really fast, then we just speed this up, and we can play it immediately, and it eats super fast. So you have this really quick feedback loop. And that was also a pretty common theme yesterday with the whole Unite, in the keynote yesterday. Besides that, we have a whole bunch of other values, which are the other config values, like speed or acceleration time. So for example, we can change the speed of the hippo to like 4 times more, and then we can immediately see how that looks like. Well, it looks like that. And like that, the artist can tweak them. And also, you can have like acceleration time and such in here, right? So, for example, a lion is really fast in accelerating, and it will be really up to speed. But a hippo might take a little bit, it might be a little bit slower. And those are things you really want to see just real time, and you don't want to like go back and forth and such. Another thing that we tried to do was to make it as easy as possible for an animator to add an animation. So we have here the list of animations, and we don't have an excited animation yet. So we want the hippo to be excited when it sees some food or something. Well, we have here the excited FBX that the animator created. And what the animator would do, it would drag it in to the animations. And then when we, let's see, we play with the hippo. Oh, again. And then here we have the excited. So we can just let it go to the front again, and let him be excited. So the point of this is that the animator can come in and really add those animations super easy without having to add, for example, a mechanism like you would have to add a state or you have to wire things up. And we really wanted to make it as easy as possible to add things, to add animations without any coder needed. And basically what this is just a glorified JSON editor, right? What happens is when we click save here, all we do is just we serialize this object to the JSON. And the only difference is that when we are in play mode, that we hook up to the config of the animal that you're playing with. So we actually look for the animal in the sandbox, and we hook up to it. And with that, we can also change the config and immediately see the results. But actually, with this architecture, that's quite straightforward. So now we have this really nice window for the animator to use. And the good thing is that because it's our own editor, that it's probably going to change a lot. A lot of the config values that we saw there, we can probably strip out. We don't need more anymore at some point. We might have to add things. Well, we can do that because, well, it's our own editor windows, and we can change them as we want.
All right. So that's our UI. And like I said, the nice thing is that if we now want to change stuff, we only have to change one single system, and it will always be in sync because it's just one system. In addition to that, we also get some more benefits, like, for example, merging becomes a bit easier. If everything is expressed in code, then Git is just a bit better at merging code than it is at merging animation controllers. And also debugging is a bit more straightforward because it's all code. You can just set a breakpoint anywhere, step in, and then see exactly what's happening by just inspecting the values or just stepping through everything that is happening. So that's our animation system. One thing I really, really like about Unity is that Unity gives you the power to create a system like that, and is super, super flexible. Depending on your game, you can also mix and match the different approaches. Like, for example, let's say you have some agents that are controlled by a very complex AI, but other players or other characters that are controlled by the player. Then you could use like a visual state machine for one, and you could use code for the others, and you can mix and match them. So Unity is really, really powerful in enabling you to really choose the system that fits your need best. The game we are creating is a mobile game. So at the end of the day, it has to work nice on the device. So once we have everything wired up, all the animations look great, we have to ensure that they also look great on the device. And since the devices are all different, especially on Android, you have to test that. There are two testing approaches we are using. It's an automated test as well as a manual testing. And I quickly want to talk about some of the challenges we faced there. In a previous project, what we did is we did regular device testing sessions, right? So in regular intervals, we would all play the game on a huge array of different devices. The problem with that is whenever we found something that was not quite right, we had to do some detective work. What change actually caused that? For example, imagine you have suddenly the frame rate on a Samsung S3 is way worse than it was before. Then you have to go through your commits and see, okay, which of these commits could have had that impact on the performance. So how do we solve that problem? What we do in our latest project is we do continuous device testing. So with every single commit, the build server will take that commit and create an automated build every single time we commit something. And that automated build will then be automatically installed on all our reference devices. And doing that is super, super simple. We have a very, very straightforward little bash script that does that for us. So first, in the first line there, we do some bash magic to get all the IDs. Then we iterate over those IDs and just install it on every device. And if you watch closely, you see this little and sign here. What that does is it will execute all those things in parallel. Because if we were to do them one after the other, that would take forever to install on all devices. Then before we continue, we have to wait for all these parallel actions to be finished, which is ridiculously straightforward. In Bash, you just wait. And then we run the game on all our devices. And that's what it looks like.
So now the game, what we call the stress test, has been installed on a whole bunch of devices. And this is mostly Samsung Galaxies. I just peeked into the other venue, and I also saw someone talking about what's the most common devices. And well, there was a lot of Galaxy devices. And I guess that's going to stay a bit like that. And what we then do is we try to push it to the maximum. So in this case, we put a lot of lions in the game, and we try to push our collision system, our navigation system, and see if the devices can handle it. But also we can put a lot of content in there and such, and we can see if there's maybe if the devices get out of memory. Now, of course, we need to find a way of tracking all of this. So usually, if you play the game, well, you can pretty easily see if you can just see the FPS. Maybe you have an FPS counter, like also we have here, and you can have a pretty good feeling of if the game is running good or not. But it would be tedious, of course, to look at all those 8 devices all the time, so we can, of course, also automate this. So what we do is we collect all of this data. So what we do is we create a tracking call to our database every second or so, and then later we visualize it in a service called Periscope Data, and that is you can use that to create SQL queries on your database and visualize them in nice graphs. We have this available at Wooga, so we have some of this infrastructure we already had, but I'm pretty sure you can also accomplish very similar things with Unity Analytics that comes for free. So this is how our dashboard looks like, where we can see a couple of graphs and also the latest build that we made. So let's peek into a little bit into the first one. So in the first one, we see vertically we see the FPS, and horizontally we see the versions over time. So this looks pretty stable, and that's, of course, good. And we think this mostly has a lot of power if we do this for a really long time, and you will see that this, well, hopefully this stays pretty stable, right? This shouldn't go down slowly. Or if all of a sudden it goes down, that means that, well, maybe the artist put in a shader that messes up all the devices, or maybe just one special device. However, this one doesn't tell the complete story. So we also have this other graph, and here all of a sudden we see that the S4 is actually going pretty bad after 60 seconds. And that's, of course, because the other graph is an average, and this one is is taking just the last test, and on the horizontal, you see every frame in the game. And now we know that once we see this build, and well, we put it on the big screen at our office, then we know, well, we should grab the S4 and we should try to fix this. And we know that immediately. We don't know that after a little while, after maybe someone says, well, it feels a little bit slow. No, we can see it. We can see there's performance problems, and we can try to fix them.
So there's one last thing I want to show you. And for that, let's switch over to the demo. So in addition to these automated tests, you also want to play the game from time to time and see if everything is the way you expect it to be. And so we have regular tests for that. Now, it's interesting how in engineering sometimes a very, very simple idea can end up saving you a lot of time in the end. And this idea is one of them. So imagine your colleague plays the game. Might be on the device, maybe in the editor. So your colleague starts the game. He makes the lion move there. Maybe over here. Oh, what was that? Then the colleague might approach me and say, OK, Heiko, I think something was weird there. I'll ask, OK, well, what exactly? Well, I don't know. It was glitching. So then I would ask, well, what did you do? And maybe he didn't do anything special. I'll do what I always do. I just clicked around. Then I would ask him if he maybe can reproduce the case. And maybe he's tried a gazillion times and did it over and over again, and the bug just doesn't appear anymore. I just did it that one single time. We've all been there. Now, he might then give it over to me, and I might also look into the thing, and then I might try for hours, and I just can't reproduce the bug. Well, what if I could? Every time we play the game, or a player plays the game, or one of our colleagues plays the game, we record everything that happened in the game in a file that we call the event stream. So here, those are all the event streams.
Still playing.
That's the one that I just opened.
It's still playing, so you have to go out of play mode.
Yeah.
Oops.
So
I can just play it.
let's open the new one that just got created. Mm-hmm. So what I can now do is I can dig into what just happened in the game. So we built this nice little window. This is a custom window we built that basically visualizes what happened in the game, that what happened in this one particular play session. And I can go in, and I can, for example, here, look at this thing. This is where the user tapped, and I can see exactly where the user tapped. And then I can see that then, OK, the lion started walking. I can zoom in. I can zoom out. And then after the walk, he did the skid. And then here, there was another tap. And then there was this turn. And what happens a lot is that you watch the game, and then you see the lion just doing something, and you ask yourself, gee, why did he just do that? And then you can open that event stream, and you can dig in and see, OK, what exactly happened there? What was the reason for the AI to move the lion there? And here, in this case, it would be just simply because the user tapped there. But it could be, for example, because the lion was hungry. Now, in this file, you not only see all these things that happen in the game, we also record all user inputs. And what I can now do is I can simply replay this file. So what is happening now is the user just tapped, and that tap gets replayed, and tapped again, and ooh, yeah, there I see the glitch. And I can also play the same thing while the timeline is open, and then I would immediately see.
Oops, went to record mode.
Play it again. No. If I play it while the event stream is open, I immediately see what is going on in the event stream, and I see, okay, there's the tab coming up, and here we have the walk that is starting. Now, the thing you're seeing right now, that isn't a movie, it's the actual code that is executing. So what I can do is I can just go in the code, and I could set breakpoints. I can immediately step through the code and see exactly what's going on, and inspect all the variables. And I might look at that code and see, oh, wait, what's that? There's a bug. This actually needs to be deducted, right? So then I can fix the bug. And what I can now do is I can simply replay the same event stream that you just saw. And by replaying it, I can then validate that I actually did fix the bug. So here you see the tab coming up. Now skid, and in a second, the second tab. Line turns. Yeah. And now the turn is to the correct angle. So, the way it works is we take all user inputs, all file inputs, and also the random seed, everything we need to reproduce that one particular gameplay, and record it into a file that we call the event stream. And we can then send around these files. So a colleague could just send me one, and I can take this file and just play it back. And what I'm seeing is exactly what he saw when he played it. And what we usually do is we just attach these files to our bug tickets. So then when I want to fix a bug, I just replay the event stream and can immediately reproduce the bug. And this way, for simple things that might have taken hours in the past, I can now fix in minutes because I can instantly reproduce it, set a breakpoint, and inspect exactly what's going on. All right, there you have it. That's our project. We first showed you how we create our lions, then how we manage our lions, then how we make our lions dance, and how then we ensure that the lions are actually dancing. If you also want to make some animals dance with us, we are actually hiring. So if you're interested, just go to wooga.com/jobs, or you can just approach us. And if you have any questions, feedbacks, or comments, you can always just reach out to us, and we are more than happy to answer all your questions. We also will stick around for a while, so if you have questions or comments now, you can also just approach us.
Thank you very much.